All right, 3, 2, 1. All right, here we go. Another 2070 video. The online section of linear algebra and matrices here at Iowa State. And today we're going to talk one of the cornerstones, fundamental, foundational ideas, eigenvalues and eigenvectors. All right, so let's motivate it with a pretty basic matrix. Here's a good old 2x2, a 1, 1, 0, 2. And here's a fun little fact about this particular matrix. Let's say I were to multiply it by the vector 1, 1. I have chosen that for absolutely no reason. All right, well, remember the way matrix multiplication works. We're going to take this row and this column and match the entries, multiply and enter, and add them together. It gets me a 1 up here, 2, sorry, the other number, and a 2 down here. And conveniently, we see something. Conveniently, pull that 2 out. The vector we multiplied the matrix by, I got back essentially the same vector. It's just being scaled by a constant. So in other words, my matrix multiplication turned into scaling of my vector. So in the eyes of this matrix, this vector is essentially the same under its action. Seems like an interesting situation. Let's make that a bit more of a formal idea. So, given a n by n, note square matrix here, a constant lambda is called an eigenvalue if I can find a non-zero vector so that a times v is lambda times v. Alright, so in math, whenever weird words show up, or words that don't exactly seem to be in our usual English parlance, a good culprit for where this came from is either German or French. Math was pretty Eurocentric when a lot of this stuff was going down. And eigen is a German word, and it, depending on the context, means essentially same or self, and that's exactly what I just pointed out. The vector v, when multiplied by the matrix A, simply gives you a scalar multiple. So the vector is essentially itself modulo a scalar. Now, something that we want to stress here is that in order to ensure eigenvalue, the vector we find, at least one of the vectors we find, has to be non-zero. Clearly, if we allowed 0, then every number would be a eigenvalue, because a0 is equal to lambda 0 is true for any possible real number. Or otherwise, maybe we'll talk about other numbers in a coming video. All right, so that is what eigenvalues are. So for another fun example, let's say I'm looking at the matrix 1, 2, 2, 4. Here I see that the vector v, I can also call an eigenvector. And if you're going to wonder if we put the word eigen in front of everything, the answer is yes, because multiplying that vector by that matrix got me a scalar multiple of the original vector. Right. So that's a good thing to keep in mind, right? Obviously, we can write this equation, and you can read it, AV is equal to lambda v, but right, really read it, right? What is it saying? It's saying that I can find these vectors so that the action of the matrix on the vector is simply scaling it. So there's some geometry buried in here. All right, so pretty natural question now that we've seen a couple of examples of this in play. Obviously, I'm generating these numbers and these vectors somehow, so pretty natural thing to ask is, all right, well, given a matrix A, how do we find these things? Can we find these things even? Do these things always exist? Ooh. A lot of questions there to unpack, and we'll slowly get there, but before we do, let's note a special case. So, like I said, oh, hey, phone going off there. Let's get a special case taken care of. So, as we noted, we're going to get a formula in the next video, but there's a special case that's worth noting because this is a slick one. If the kth column of your matrix just so happens to be a scalar multiple of the kth standard basis element, then you know lambda is an eigenvalue immediately. You don't have to do no effort required. And the reasoning for this is because multiplying by the standard basis element, and we've pointed this out, multiplying by it will isolate your kth column. So if your kth column is already a scalar multiple of that, then we see that, hey, I have multiplying this vector by that matrix gave me a scalar multiple of the same vector. So lambda, indeed, is a eigenvalue. The standard basis elements are non-zero. There we go. So, for example, here is a 3 by 3, and if I pay close attention to that second column, I see that it's 6 times the standard basis element E2, and I can immediately tell you, hey, 6 is an eigenvalue. Great. So this is a good thing to keep in mind. This gives you a good way of keeping an eye out for quick eigenvalue computation. I always thought this was a neat little thing. And again, reminding ourselves that there are certain matrix multiplications that are very powerful. Multiplying by the standard basis elements is one of them. All right. Now, given an eigenvalue, then the elements, so that AV is equal to lambda V, are precisely the things that live in this null space here. And we call this the eigenspace, because it's a subspace associated with eigen things. And anything in here we'll call an eigenvector. We've already used the word eigenvector, but let's formalize it a little bit more. The elements of this are the eigenvectors. So given a matrix A, you're interested in solving AV equals lambda V. So if you have your eigenvalue, then finding the V's just amounts to getting a basis for this null space. And it's worth noting that this null space has to be non-trivial. Right? There has to be non-zero vectors in this set. That's the whole conceit. Given an eigenvalue, there is a non-zero V that works. And so it has to be in this null space, so my null space, note, always non-trivial. So in particular, that matrix is not invertible. Right, so let's wrap things up by actually computing a basis for this eigenspace. So let's revisit this matrix. We already know something about it. We know 6 is an eigenvalue. Alright, so the eigenspace, again, will be the null space of that matrix, so I just need to figure out the V's that satisfy 6 minus A minus 6I times V is equal to 0. Alright, so we subtract 6 off the diagonal, because that's what multiplying the identity matrix and then subtracting a matrix will do. We subtract 6 off the diagonal, and from here we'll read off a couple of equations. Now, we know something about this particular system. We know that I cannot solve this uniquely, because my matrix fails to be invertible here. So I know I'm going to find free variables. Now, obviously, we can, of course, get the reducer echelon form of this, but I always find for eigenspaces it's a little bit easier just directly work with the equations. Because, as you can see, I have two equations that are essentially the same thing, and that typically always happens. But anyway, we can see with the first and second equations that we're going to get something a little interesting. So, for example, multiplying this by -7 and adding to that, we'll get rid of the V1s, but then I'll have a V3 by itself, and thus getting V3 is equal to 0, and thus V1 will be 0, and there you go, your vector V has to be some multiple of the vector 0, 1, 0. V2 never showed up in any of those equations, so V2 is free to do whatever it wants. V1 and V3 were locked down at 0. And thus, we have a basis for our eigenspace. Pretty cool. Alright, so now we've seen if I have eigenvalues, I can get a basis for the null space of that matrix. Again, something we've done quite often. But now, we need to address the question of, well, how the hell do I even get these eigenvalues to begin with? I guess we'll find out in the next video.